Hello, my name is Nima, and with Mahdi, we will be presenting FairEM360, a suite for responsible entity matching. Entity matching is a very important data integration problem studied for many centuries. In this problem, given two collections of data entries, the goal is to find all pairs of entries that refer to the same real-world entity. Fairness in entity matching is an important problem. To highlight how unfairness in entity matching can lead to potential problems, consider a case of airline security where a passenger list is matched against a no-fly list. A false positive error results in inconveniencing the passengers by being fed their questions or even potentially missing their flight. False negatives could lead to allowing a potential danger aboard the flight. Due to many reasons, such as inherent similarities in the naming conventions of some countries or the overrepresentation of a group of people in the list, such as no-fly lists, if the matcher makes mistakes that are systematically correlated with a sensitive attribute such as ethnicity, it will be unfair towards that group. Therefore, we introduced FairEM 360, a suite for responsible entity matching. Next, Mahdi will go over the demonstration of the system.
Let's get started. First, we will select the dataset to work with. FairEM360 supports various data ingestion methods. We can choose from existing datasets, upload our own dataset, or upload matching results. In this demonstration, we will proceed with an existing dataset called Faculty Match. This dataset contains information about faculty members and their affiliated countries. Next, we will select the matchers that we want to train and evaluate on the chosen dataset. We have a variety of matcher options, including both neural and non-neural approaches. Each matcher has a description that appears when you hover over its name. For this demonstration, we will explore the results of all neural matchers and one non-neural matcher. We will then initiate the training process and wait for the matchers to run. Once the matching process is complete, we can use the system's auditing functionalities to assess fairness for each group. The control panel allows us to configure various parameters that influence the fairness analysis. First, we need to select the sensitive attribute, which is a characteristic that could potentially be discriminated against. Then we choose the disparity calculation type, which determines how fairness is measured. We will use the division-based method here. Next, we select the fairness metrics we want to consider. Our system offers 5 metrics, and hovering over each metric provides a description of its calculation method. In this case, we will select true positive rate parity and positive predictive value parity. We'll also set the matching threshold, which specifies the minimum similarity score required for a match. A higher threshold leads to stricter matching policies. We'll keep the default value of 0.5. Finally, we need to define the fairness threshold, which represents the acceptable level of disparity between groups. We will set this value to 0.2. Lastly, we can choose the fairness paradigm, which determines how fairness is analyzed across groups. We can analyze fairness using a single paradigm, a pairwise paradigm, or both. We will start with a single paradigm approach here. After configuring these parameters, we can initiate the analysis and wait for the results. The results will be presented in a bar chart format. Bars that exceed the fairness threshold indicate unfairness for a particular matcher group combination. For example, if the bar for deep matcher and the Chinese group in the true positive rate parity metric is above the threshold, it suggests that the deep matcher performance is unfair for Chinese faculty members. The system also allows us to view results for pairwise and single paradigm and to focus on a specific group or metrics. To gain a deeper understanding of the reasons behind fairness issues, we can click on a specific bar chart element. This will reveal additional details, such as random samples of the dataset for the chosen metric. For instance, if we investigate the case of low true positive rate parity, we might see examples of false negative matches. These examples could reveal that the inherent similarity of names from a particular group, for example Chinese names, has caused the matchers to miss some valid matches. Additionally, our system provides coverage matrices to illustrate the proportion of data points from each group included in the matching process, and confusion matrices to offer more detailed insight into the matcher's performance. After identifying fairness issues, we can leverage systems' ensemble matching capabilities to create a combined matching strategy that mitigates bias while maintaining performance. Our system will automatically explore all possible matcher assignment to different groups and present the results for each combination. The left-hand side of the screen will display detailed information about each metric value for all groups for different matchers. Additionally, a fairness performance trade-off chart will be displayed. This chart allows us to visualize the trade-off between fairness and performance for each ensemble. The x-axis represents unfairness, with lower values indicating fairer ensembles. The y-axis represents performance. Each point on the chart corresponds to an ensemble strategy. Hovering over a point reveals the associated performance and fairness values. The Pareto frontier highlighted on the chart represents the set of non-dominated strategies that offer the best possible fairness performance trade-off. By analyzing this chart, experts can select the ensemble that best suits their priorities, considering how much fairness or performance they are willing to sacrifice. Let's focus on positive predictive value. Here, we can see that all points on the Pareto frontier represent non-dominated values. Since the performance gain between these strategies is negligible, we can prioritize fairness by selecting the ensemble with the lowest unfairness value. By clicking on this point, we can see the specific matcher assigned to each group and the resulting disparity scores. This helps us understand how the ensemble mitigates bias while maintaining good overall performance. In summary, this demonstration showcased how FairEM360 can be used to select a dataset and train multiple matchers, Evaluate the fairness of each matcher for different groups, analyze the root causes of potential bias, and also identify and apply an ensemble of matchers that achieve the desirable balance between fairness and performance. FairEM360 empowers users to identify and address bias in entity matching tests, promoting fairer and more trustworthy results. Thank you for watching.